Hello everyone, and welcome back. Today we continue our exploration of optimization methods and introduce a very famous numerical scheme that can be used to approximate the solution for optimization problems. Today we're only going to be focusing on the one-dimensional, what is called Newton-Raphson method, for approximating the zeros and optimal values of objective functions. And once we have a firm understanding and also the implementation of the one-dimensional Newton-Raphson method, it will make the extension to multi-dimensions and optimization with the Newton-Raphson method a little bit later a lot more easier and also more intuitive once we make that leap. So let us first off start off by asking the primary question that the Newton-Raphson sometimes answers for us. So suppose that we want to find the zero of some one-dimensional function. In particular, let us suppose we have this curve in orange, for example, and let's assume that it crosses the x-axis somewhere, right? So our goal is to estimate the value of that x-intercept, where some people refer to this as the zero of a function. So we're going to be calling this point, for example, x star. Right? So how does the Newton-Raphson iteration work? So the Newton-Raphson iteration starts off with what is called an initial guess. So the initial guess, which we're going to be representing by x sub 0, should be ideally close to the true solution. So if you have a graph of the function that you're working with and you want to approximate a particular zero, which is very important when you have multiple zeros of a function, then choosing something that appears to be close to the true answer definitely is going to help the Newton-Raphson method converge a lot more quickly. So let's assume that in this picture, our initial guess is located right here. So let's pretend that that is our x0. So what the Newton-Raphson method does is it goes up to this particular curve and it analyzes the curve at that point. So if that is x0, that means the height of that curve at that point is also going to be f of x0. And what we can do, if this function is differentiable, and let's assume that it is, then the derivative at x0 fx0 also exists, and that means we can draw, for example, a tangent line to that curve at that point. Now, as you can see, that line, at least in this particular example, crosses the x-axis at a point closer to the goal of this method. That's a lot more closer than our initial guess. So what we're going to do is we're going to call that new point, that intersection for which our red line crossed the x-axis, we're going to be calling that x1, and then we're going to repeat that process until, hopefully, the sequence of iterations converge to our true zero of the function, right? So as long as your function is nice and your initial guess is reasonable, the Newton-Raphson method typically will converge, and we'll discuss a couple issues that the Newton-Raphson method might encounter if you choose your functions a little bit more cleverly. So let's focus on this line in red with a little bit more detail and see if we can find an equation for that x1 given some arbitrary x0. So what we're going to do is we're going to let L represent the point that passes through the point x0, fx0. So that's that point right there. And this line, we want to have a slope of f prime of x0. So we're going to assume that this function f is differentiable. If it's not differentiable, then you can't apply the Newton-Raphson method on it, at least not in the classical case. So what is the equation of this line? So generally speaking, you can represent the equation of a line in the form y is equal to mx plus b. That's the elementary perspective of this. So we know what the slope is. The slope is assumed to be f prime of x0, so we can actually just replace that here. So we have y is equal to mx plus b. So the next thing that we need to figure out, okay, well, what is b? Well, we know what a particular point xy is on this line, so we can actually just substitute them in here, and then we're going to get what? So that means b is going to be equal to y minus m times x, right? So that is our intercept of our line L. So we can rewrite this expression as the following. We can write that as y is equal to mx plus b. Right, and that is our equation. And we can actually write this in a nicer way because notice that we do have a common factor of f prime x0 in the first and the third term. So we can write this in a more traditional fashion. So the way we're actually going to present this is y is equal to f of x0, so that term, and then we're going to have plus f prime of x0 times x minus x0, right? And if you're familiar with Taylor series from one-dimensional calculus, you should realize that these are just the first two terms of the Taylor series centered at x is equal to x0. And some people will also refer to this as the linearization of f at x is equal to x0. Okay? So now we have the equation of the line L. Now the next thing that we need to figure out is where this line crosses that x-axis, because that is going to be our x1. Okay, so when y is equal to 0, now one may ask, well, what guarantees that this line does cross the x-axis? You can think about that momentarily, but eventually I'll answer that. So when y is equal to 0, we're going to call that solution x1, right? So let's solve that equation for x when y is equal to 0. So once we have that, we're going to have 0 is equal to f of x0 plus f prime of x0 times x minus x0, and our goal is to solve this equation for x. So once we rearrange just a tad bit, you should see that this is just going to be equal to what? So move that to the left-hand side, divide by that. So we're going to assume that f prime of x0 is non-zero. So we're going to have minus f of x0 divided by f prime of x0 is equal to x minus x0, and keep in mind that's going to be equal to our x1, and then add x0 to both sides, and then we are done. So we see that x1 is going to be equal to x0 minus f of x0 divided by f prime of x0. So that is going to be our new approximation to the true solution, x star. Now, how do we find x2? Well, you just replace x0 with x1 and x1 with x2, and that gives you the formula for x2. So now we can state formally the Newton-Raphson iteration method. So the Newton-Raphson iteration method pretty much is the generalization of this formula. So xk plus 1 is going to be equal to xk minus f of xk divided by f prime of xk, where k is equal to 1, 2 onwards, and x0 is a initial guess, ideally in some neighborhood of the true solution. So under certain conditions, this sequence should converge to the true solution. So let's just state that vaguely. So under certain criteria, which we won't get into, that's more of a theoretical discussion that I don't want to discuss at the moment, one can show that xk does converge to a 0 point as k tends to infinity, right? And of course, one requirement, so one obvious requirement, is that f prime of xk cannot be equal to 0 for all k in the natural numbers. In particular, f prime of x0 cannot be equal to 0. So yes, you can technically choose any initial guess. It might not converge, but one requirement of that initial guess is the derivative of f at that point cannot be equal to 0, else you can't use our Newton-Raphson method anyway. So what do we mean by the derivative cannot be equal to 0? So keep in mind, when we have a differentiable curve or surface, if we take the derivative and we're equal to 0, that means that these lines are tangent to the curve at maxima, minima, and curvature points, for example, in y is equal to x cubed, so a point such as that. So if they're maximum or minimum, that means the tangent lines are parallel to the x-axis, which means they never cross the x-axis. So that's a problem. That means you can't get your next iteration of the Newton-Raphson iteration method. Now, a couple other potential issues that may arise in the Newton-Raphson iteration process. So I'm just going to draw a couple graphs here. So let's assume we have a function like this. Arctangent would be a function that sort of has this type of property. So there does exist points on this curve where, for example, if you draw the tangent line here and it crosses there, and then you go up and you do that point and it sort of crosses there, you're going to get into this cyclic pattern where you have x0, then it's going to go to x1, and then x1 is going to x2, but x2 is the same as x0, and then x2 is going to go to x3, but x3 is the same as x1, and so on. So you get the cyclic pattern, and that's definitely not a good thing. Another picture that we can also illustrate with this, for example, let's assume that we have that. So it's not quite equal to 0, but the tangent line definitely goes off to some really big number. For example, like 5 times 10 to the 3001 or something like that, right? A lot of computers can't handle stuff like that, so it will treat it as infinity. So even though the derivative at this is not equal to 0 theoretically, it can be viewed as numerically equal to 0. And that's going to, of course, create some issues. And another issue where the Newton-Raphson method definitely is going to give you some problems is, for example, if you have like y is equal to sine of 1 over x, where you have just a bunch of nonsense going around, for example, 0, right? So clearly discontinuous at 0, and it's just going to, give you some crazy stuff as you get closer to 0, which is definitely a bad thing, okay? Like, which x-intercept are you converging to, since there's obviously infinitely many, but those are 3 of the most common issues where the Newton-Raphson iteration method actually is going to give you some issues. But as long as your function is well behaved, then the Newton-Raphson typically will do just fine. Let's assume that one of the problems that we get posed with, whether it be theoretical or even an application, is that we need to solve some equation for some variable. For example, we seek to optimize profit or minimize cost or something like that, and the solution to this equation actually solves those problems. So let's pretend that that particular function we're trying to solve is x times x squared plus 1 is equal to 1, and let's assume that the solution we're looking for is a real number, nothing complex or nothing spooky like that. Right? Now, of course, not all equations have what we call elementary solutions, and sometimes they don't even have algebraic solutions. So sometimes the best we can do would have to be a numerical solution until some, progress can be made to represent the true solution in some useful analytic form. So every time you have an equation like that, we can actually use the Newton-Raphson iteration to solve it by treating it as, or some manipulant of it, as a function for which we seek to find the zero of. So if we slightly manipulate this equation just a tad bit, we can write this as, for example, x cubed plus x minus 1 is equal to 0, right? So what we can do is we can treat this function as our f, so that means we seek to find, the zero, or possibly zeros, of the function f of x is equal to x cubed plus x minus 1. So this is what we're going to be applying the Newton-Raphson iteration to. Now, we first off need an initial guess, right? So our initial guess needs to be reasonable, so maybe we can generate a graph of that, maybe use some computer software, or just plug in a bunch of points, get a table of values, just to get some working knowledge of this. So one can show that that point is going to be 0, and that point here is going to be equal to 1. So our true solution, call it say x star, lies between 0 and 1, right? So for example, we can choose x0 to be 1, we can choose x0 to be 0, maybe even 1/2, right? But if you're doing it by hand, definitely choose some nice numbers because the calculations definitely get ugly very, very quickly if you do it by hand. So this is our function f of x is equal to x cubed plus x plus 1. So if we do the derivative of f via the power rule, that's just going to be 3x squared plus 1 plus 0, or just 3x squared plus 1. So if we plug in, for example, f prime of 1, that's going to give us 3 times 1 squared plus 1, which is going to be equal to 4, which is not equal to 0. Therefore, we can use 1 as our initial condition, and of course you can use 0 as your initial condition too, but I'm just going to choose 1 just for excitement purposes, right? So what we're going to do is we're going to choose x0 to be 1, and then from here we're going to let the Newton iteration do the rest for us, right? Now, is 1 the best initial condition? I'm not claiming that, but as long as it's relatively close to the solution and the derivative is not 0 there, it should work out fine. So we've already found, or one can find, that f of 1 is going to be equal to 1, and f prime of 1 we've actually already found to be equal to 4, which is not 0. So that means what? So keep in mind x1 is going to be equal to x0 minus f of x0 all over f prime of x0. So we chose x0 to be equal to 1, minus f of x0 was also 1, and f prime of 1 was going to be equal to 4. So 1 minus a fourth is equal to 3/4, which as a decimal is equal to 0.75. Okay, so that's the first iteration of the Newton-Raphson iteration method. So we can go ahead and do that again. So for example, x2 is going to be equal to x1 minus f of x1 all over f prime of x1. So we're going to take 0.75, put it there, plug it into f, plug it in our derivative, evaluate that expression, and one can find that that's going to be approximately equal to, and we'll give you a few decimals here, or you can try it out yourself, 0.68, 604, and then 65, with a bunch more decimals. And if you repeat this iteration, for example, x3 is going to be equal to 0.68233396. x4 is going to be approximately equal to 0.68233278, and we can continue onwards. Now, notice, if you look at 0.75 and 0.68, the only common digit would be the whole number digit 0, right? So that would imply that if you trust the Newton-Raphson iteration method, now trusting it in the early stages definitely not recommended, but if you do trust in the early stages, that implies that the x-intercept is between 0 and 1. Now notice once we go from x2 to x3, notice that we have some common digits here. Notice we have 0.68 and 0.68, so we should be looking for a true solution somewhere between 0.68 and 0.70, somewhere in that realm. Also, even notice between x3 and x4, notice we have 0.6823 and 0.6823, right? So that appears to be converging to some number. So for example, if we go to x5, that's going to be equal to 0.6823278 with a bunch more digits, which all match. In particular, if you continue this on and on and on, one should be able to show that the true solution is approximately equal to 0.682327803828, which does match the first few digits for which the Newton-Raphson gives us. And notice that it actually gets very, very close to the exact solution in only a few iterations, which is one of the reasons why the Newton-Raphson iteration method is so popular for solving the zero problem for differentiable functions. From the optimization method perspective, finding zeros of functions actually isn't a more useful perspective. Instead, one may just focus on the problem of optimization, and one actually can show that these two problems are very, very closely related. So let's assume that we want to optimize some single variable functional. Let's call it fp to make sure it's not confused with the function that we were finding the zero of. So if we want to optimize this 1D function, then clearly in this particular picture, if this was the function that we're working with, therefore our optimal solution x star is going to be located right there. Right? Now, what is so special about this? And then keep in mind, this could be a maximum or a minimum, right? So if we take the derivative of this differential function fp at x is equal to x star, keep in mind that the slope of the tangent line at that particular point is going to be equal to 0, right? So the slope of that line, f prime of p, or f prime of x star, is going to be equal to 0. Now, this should look familiar because if we're trying to find the value x star that makes some function equal to 0, in this case that function is the derivative of the function we're trying to optimize, we can apply the Newton-Raphson iteration on that. So therefore, we can view this as optimizing FP is equivalent to finding the zeros of F prime P, right? And P is a subscript here denoting what we call the primal function that we seek to optimize, right? So if that's the case and we're trying to find the zeros of P, that means we can write the Newton-Raphson iteration method in the following way. So xk plus 1 is going to be equal to xk minus f prime P of xk divided by f double prime P xk, and as usual, x0 will be our initial guess. All right, and we know how to conduct that sequence. But a downside is if we want to do this by hand, we have to calculate the derivative and also the second derivative of that function. But if the function is very, very easily, then that shouldn't be an issue. Now, although since we learn a bunch of rules in single variable calculus, such as the product rule, quotient rule, chain rule, and maybe some of your teachers may even gave you, some 5-page derivative problem for which required a lot of algebra in order to find it. Now, even though you could theoretically get the derivative or the closed form representation of any differentiable function, it's sometimes not easy, practical, or even computationally possible if the function f or fp is extremely complex, right? And if we approach that from the optimization perspective, we have to find the derivative and also the second derivative, which could be even more annoying. So a good thing we can do is possibly approximate the values of the derivative and the second derivative if we're using the optimization approach via, for example, forward, backward, or central difference approximations for those differential expressions. So let's just quickly review the central difference approximations. So central difference approximations to f prime and f double prime, just in case you are not already aware of that. So typically the forward difference approximation is what is typically taught in a calculus course, f of x plus h minus f of x over h, where h tends to 0, and the approximation form is where we make h really close to 0 but not tending to 0. So the central difference approximation for f prime of p at a particular x value is going to be approximately equal to 1 divided by 2h times fp of x plus h minus fp of x minus h, where h is some number close to 0, like 0.0001 for example. And one can also show that the second derivative at x can be also approximated via the expression 1 divided by h squared times fp x plus h minus 2 fp of x plus fp of x minus h, again where h is arbitrarily close to 0. And you can ask, well, can I use the forward and backward difference approximations to f prime and f double prime? The answer is of course, but you should be able to show, if you're familiar with these things, that the central difference approximation is a lot more accurate, generally speaking, for the arbitrary function compared to the forward and backwards difference approximations. So if that is the case, that means we should be able to rewrite, for example, the zeros perspective of the Newton-Raphson iteration method. So keep in mind, let's just refresh. So for finding the zeros of some function, for example, f, xk plus 1 was equal to xk minus f of xk all over f prime of xk. So if we represent this in the numerical perspective, that means xk plus 1 is going to be approximately equal to xk. So the 2h is going to reciprocate since f prime is on the bottom. So that's going to be minus 2h times the expression f of xk, which was originally on the top, and then we're going to have, for example, f of x plus h, and then minus f of x minus h on bottom, where h is chosen to be something approximately equal to 0. All right, so that is that particular expression, which is actually very, very nice. And more importantly, what about the optimization perspective? So let's go ahead and derive that. So the optimization of, for example, fp was xk plus 1 is equal to xk minus fp of xk prime divided by f double prime p xk. So if we approximate the first and second derivative with a central difference approximation, we have some h's cancel out, and you should be able to show that this is going to turn into xk plus 1 is approximately equal to xk minus h over 2. On the top we have the derivative interior, so fp x plus h minus fp x minus h, and on the bottom we have that second order interior. So fp x plus h minus 2 fp of x, and then plus fp x minus h, and that is the central difference representation of the Newton-Raphson iteration for both the zeros and the optimization perspective. And if you're familiar with any programming languages, then those are ready to calculate, where again, h is chosen to be something close to 0. So I hope you enjoyed this introduction to the Newton-Raphson iteration method. Keep in mind these are only for one-dimensional functions, but we will revisit the Newton-Raphson iteration a little bit later and generalize this to the multi-dimensional case. So I hope you enjoyed. Take care.